This session is about TCP/IP protocol suite. First, we will see what is TCP/IP model. Then, we will learn about flow of data in TCP/IP model. After that, we will look at layer communication types. Finally, we will understand each layers of TCP/IP model and its function. TCP/IP stands for Transmission Control Protocol and Internet Protocol. It's not just one protocol, it is a collection or suite of protocols. This protocol helps computers to talk each other over the internet. And why do we call it a protocol suite? Because it is made up of multiple protocols. All works together like a team. Each protocol in this team has a specific job and they are arranged in layers. TCP/IP follows a hierarchical model. But what does that mean? It means the layers are arranged step by step, like a staircase. Each layer depends on the one below it. That is, the upper layers depends on the lower layers to do their job. Each layer has a specific job like sending, routing, or delivering data. Application layer sends the message. Transport layer breaks into segments. Network layer routes it. Data link and physical layers handle actual delivery. Now let's break down the two main parts of TCP/IP. IP, Internet Protocol. It finds the best path for data to travel. It handles addressing and routing. Addressing is like a home address for devices. Routing means choosing the best path to reach the destination. IP is like delivery route planner. TCP, Transmission Control Protocol. It makes sure the data is delivered correctly and completely. It handles sequencing, acknowledgements, and error checking. Sequencing means keeping data in order. Acknowledgement means receiver confirms it got the data. Error checking means making sure data isn't lost or broken. So TCP is like a person who carefully packs and checks every box before delivery. So IP finds the way and TCP makes sure everything gets there safely. Together they make internet communication possible. TCP/IP is backbone of internet communication. It allows devices to talk each other from end to end. The OSI model is mostly theoretical, while TCP/IP is practical framework used in real networks. It was first developed in 1970s by DARPA for ARPANET project. And today, TCP/IP is global standard used across all internet connected systems. The original TCP/IP protocol had 4 software layers built upon the hardware, but now it is often seen as having 5 layers. Let's understand how data flows between two computers A and B using the TCP/IP protocol suite. Consider a scenario. Computer A wants to send a message to computer B. Computer A is source, computer B is destination. Between them, we have switches and router. This network has 3 LANs connected via switches and router. Now how data flow is, computer A creates a message in application layer. It moves down through transport, network, data link and physical layer. Then it passes through switch 1. It only checks the frame info and forwards. Now the router reads the IP address and decides next hop, and sometimes it may reframe. Now switch 2, again it forwards the frame. Finally, the message reaches the computer B where it goes up layer by layer to application. Each device interacts with different layers based on its role. Both hosts use all 5 layers. The source host creates a message in the application layer and sends it down through the layers to reach the destination host. The destination host receives the message at physical layer and processes it through the layers up to the application layer. The router only uses 3 layers because it does not handle transport or application layers when routing. It operates at network layer and connects to multiple link and physical layers depending on how many links it has. Each link may use different protocols. For example, the router in the figure connects to 3 links, but the message from source A to destination B only goes through 2 links. And each of these links may use different protocols. A link layer switch, on the other hand, only operates at two layers, which are data link and physical layer. Even though each switch has two connections, they are within the same link and use the same set of protocols. Therefore, in contrast to router, a link layer switch operates only at one data link layer and one physical layer. But now let's try to understand how different layers communicate during this journey. In networking, we use two important concepts to explain this flow, which are end-to-end communication and hop-by-hop communication. First, end-to-end. It means the data travels logically from source host to destination host. The data is handled by top three layers, which are application, transport, and network layer. Even though it passes through router and switches, these middle devices don't touch the actual data created by the app. They just helps to move forward. So the app on computer A directly talks to the app on computer B. That's why we say end-to-end communication. Now let's come to hop by hop. It is used by last two layers of TCP IP model, which are data link layer and physical layer. These layers don't send messages from A to B directly. They only handle one step at a time. Like computer A to switch, switch to router, router to next switch, and so on. Every time the data moves from one device to the next, and that is called hop. So these layers handle each hop step by step. For example, you write a letter, your friend reads it. Only you two know the meaning. This is called end-to-end. Hop by hop means you write a letter, the postman picks the letter and pass through sorting centers, move it step by step, and they don't read. Now let's understand how data units stay same or change as it moves through the layers in TCP IP model. Each layer in TCP IP protocol suite creates a specific data unit like message, segment, packet, frame, and bits. If the data unit stays the same from one hop to another, we call it as identical object. Now look at the diagram. It shows the second principle of protocol layering, which is discussed in previous video. This diagram shows the identical objects at each layer for different devices. From the diagram, we can say, in this case, the identical objects exist between only two hops. Because at network layer, the router might break the packet into smaller pieces called fragmentation. As a result, it sends more packets than it received. After understanding logical communication, now we will discuss the role of each layer. First, physical layer. The physical layer is responsible for transmitting individual bits across the link. Even though it is lowest layer, the communication at this layer is still logical because there is a hidden layer called transmission medium. Transmission medium is like cables or air. Two devices are connected by transmission medium. The transmission medium carries electrical or optical signals, not bits. So the bits received in a frame from data link layer are transformed and sent through transmission medium. But we think the logical unit between two physical layers in two devices is a bit. There are various protocols that convert bit into signals. We will discuss them in upcoming videos. Now, data link layer. The internet consists of multiple links like LANs and WANs connected by routers. These routers determine the best link for data to travel. Once the next link is chosen, the data link layer moves the datagram across that link. It can be wired or wireless. The data link layer encapsulates the datagram into a packet called frame. TCP IP does not define any specific protocol for data link layer, but it supports all standards and proprietary protocols. Some protocols offer complete error detection and correction, whereas others provide only error correction. After that, network layer. The network layer connects the source and destination computers. It handles host-to-host communication and routing of packets through routers. The main protocol at this layer is Internet Protocol. This protocol defines the packet format called datagram and structure of addresses. IP is connectionless protocol. It does not provide flow control, error control, or congestion control. If these services are needed, the application must rely on transport layer. The network layer also includes protocols like ICMP, IGMP, DHCP, and ARP. ICMP is used for reporting routing issues. IGMP is used for managing multicast groups. DHCP is for assigning network addresses. And ARP for finding link layer addresses. Then we have transport layer. Transport layer provides end-to-end communication. It takes message from application layer and encapsulates them into a transport layer packets called segments or datagram and sends them to the destination host. This layer separates the tasks and allow different protocols to be used based on the application needs. The main transport protocol is Transmission Control Protocol. TCP is connection-oriented protocol and it establishes a logical connection before data transfer. It provides flow control, error control, and congestion control. In contrast, the UDP is connectionless protocol. It transmits user datagrams without establishing a connection. The UDP is another common protocol used in transport layer. Each packet called a datagram is treated as a separate independent message. That is, in UDP, each user datagram is independent, meaning it does not depend on any previous or following datagrams. This independence is a key feature that defines UDP as a connectionless protocol. UDP is designed to be a simple protocol which results in minimal overhead. Minimal overhead means the protocol is designed to minimize the amount of data required for transmission. It is beneficial in the scenarios where bandwidth is limited. UDP sends data faster because it does not add extra information or checks. So it is quick and uses less processing. And then there is a new protocol called SCTP, Stream Control Transmission Protocol. It combines some features from both TCP and UDP. This protocol is designed to support multimedia applications like video calls, voice calls over the internet, and other real-time multimedia apps. The transport layer helps the application layer, which means it takes a message from an application on sender's computer and delivers it to the correct application on the receiver's computer. It gives an end-to-end communication between applications. You may ask, why do we need transport layer if application layer already sends messages end-to-end? The answer is, each layer has different jobs. The transport layer and application layer are separated to make the system easier and more flexible. The transport layer is independent. It handles delivery tasks and works separately from the application layer. For example, you are sending a WhatsApp message to a friend. Your phone has WhatsApp application. This is application layer. But how does the message travel safely across the internet? And that job is done by transport layer. WhatsApp, that is application layer, creates a message, but it cannot send it directly. So it gives the message to transport layer. Now the transport layer sends the message to your friend's phone. It makes sure the message reaches your friend's WhatsApp application, not to some other app. So application only creates a message. The transport layer is responsible for delivery, like a postman. And finally we have application layer. The application layer connects two applications directly so that they can exchange messages as if there is a bridge between them. This layer provides a communication between two processes or programs running on different computers. One process sends a request to another process and receives a response. The logical connection between two application layers is end-to-end. The duty of application layer is process-to-process communication. The application layer has many built-in protocols. In addition to standard protocols, users can create their own programs or processes. This means they can design their own way of sending messages or data between applications. For example, you can write your own custom programs like chat app or file sharing tool. These two programs can use sockets to talk to each other using the application layer. The standard protocol used in application layer includes HTTP for browsing websites, SMTP for sending emails, FTP for transferring files, Telnet and SSH for remote login, SNMP for managing networks, DNS for finding IP addresses,